Well, greetings, mathletes, and welcome back. Um, so this is the second part of our discussion of multi-stage experiments. And the second part here, I'm just going to show you some different ways to organize this information. In some ways, try that again. So some ways of representing them make certain things easier than others. And so that's kind of what I want to take a look at here. So what I want to look at this time is a tree diagram. Oh, yeah, it turns out this works a lot better that way. Okay, a tree diagram. Now, these tree diagrams get used for lots of things. Um, Probably one of the most obvious places it gets used in math is in finding prime factors, right? You make a tree for that. It's actually very similar, except for this is a decision tree, right? So we're going to map out all the possible decisions we can make. So the way we work this is we look at each experiment as a choice. So in the first part of the experiment, which is the first draw here, right? And since we only have black and white marbles, we only have two choices. It's either going to be a black marble. Oh, excuse me. Let's organize that slightly differently. It's either going to be a black marble or it's going to be a white marble, right? If I draw a second time, I still have that choice. Because if I draw a white marble, right, the second marble, the second choice here, it could be a white marble or it could be a black marble. Down here, if I draw a black marble on the first draw, this could be a white marble. Or the second draw could be a white marble or it could be a black marble. Okay, now here's how this ends up getting used. Okay, so for the first choice here between a white and a black marble, we can work out the probabilities of each thing happening. So we're actually not paying any attention to the second choice right now. We're only looking at the first choice between white and black. And on the first draw, there are 3 white marbles and 7 black marbles, which means the probability of getting a white marble would be 3/7. And the probability of getting a black marble, oh, not 3/7. Until I'm getting tired here. Try that again. 3/10. There we go. Or 0.3, right? And the probability of getting a black marble would be 7/10. Let's make that look more seventh-y. Right? So that's our first choice. Now, if I draw a white marble on the first draw, right? So we're not even looking at the bottom part of this right now. Let's assume that we have already drawn a single white marble out of the bag. Since this is without replacement, it stays out of the bag for the second set of choices. So if I pulled a white marble out of the bag, the probability of getting a white marble on the second draw, well, there's going to be 2 white marbles now. And now there's 9 marbles total in the bag. So that's actually 2/9. And let me doctor up my handwriting here. Right? It's actually 2/9 for that choice. Now, if I'm going to choose a black marble, I haven't changed the number of black marbles, but I have changed the number of marbles in the bag. So there are still 7 black marbles if I've chosen a white one in the first choice. However, there are only 9 marbles left in the bag, right? So we have those 2 choices. Now down here, if I want to fill that out, if we've already drawn a black marble, then we have 2 choices here. We can draw a white marble or we can draw a black marble. The probability of drawing a white marble, since we've only pulled a black marble out, we haven't changed the number of white marbles. I'm going to write this one over here because it's going to reduce. There are 3 white marbles left, but there are 9 marbles left in the bag. So that probability is now 1/3. So this is 1/3. And then down here, if I draw a black marble on the second, the probability of that happening the second time, if I've drawn one on the first draw, Um, let's see here. There were 7 marbles to start, black marbles to start with. So now there's 6 of them. And I've also reduced the number of, oh, excuse me, the number of marbles in the bag by 1. So now it's 6/9, and that makes that 2/3. So this one would be 2/3. Okay, so what this represents here is actually a probability distribution. I can choose any endpoint here, and I can see what path would take me there. So, for example, if I start here and I want to see the probability of getting a white marble on the first draw and a white marble on the second draw, I follow this path. Let's see, white marble, that's 3/10. And if I go from white marble to the second white marble, I multiply that by 2/9. So the probabilities that I've written on the edges of that path are the ones that um, are going to be the ones that I multiplied together. And so looking at this would give me 6/90 if I multiplied those two fractions out. And if I reduce that, let's see here, if I reduce that by 3, I would get 2/30, so it's 1/15. Right? So what I just computed was the probability of getting 2 white marbles when I draw. Okay, now let me back some of this up. Ooh, I'm going to have to back up quite a bit. I wanted to get those lines off the drawing. There we go. Okay, so now, let's see, we're all selected here. Good. So let's see if we can compute a different probability. Let's see if we can compute the probability of drawing a black marble on the first draw and a white marble on the second draw. Okay, so I'm just going to follow the path that takes me to a black marble and then to a white marble. So I'll go here. So that takes me to a black marble. That gives me 7/10 for my first factor. And then if I want to go black then white, that means I follow this path. That means I'm going to be multiplying by 1/3 after that. So if I multiply these guys together, the probability of drawing a black then a white marble is going to be 7/30. Right? So just over 20%. And so in this way, you can actually compute the probability of any possible outcome. You can go 2 black, 2 white, white then black, black then white. You can actually walk through the whole thing and figure out every probability that you need. And that's actually what makes something a probability distribution, is that it covers every possible outcome, and you have the probability for each of those outcomes as you go. Sometimes it's represented in a table, sometimes it's represented in a formula, but anything that gives you every possibility and the ability to compute the probability for each possibility makes it a probability distribution. Okay, so I want to go ahead and take a look at another example now. So let's go ahead and erase all this. There we go. Okay, and then for our last example here, this is going to be an example of using a table to figure out your probabilities. And so we're going to actually create a little table. One of the things I want to point out about this particular example, there are 2 major events that we can look at in here, right? Being someone who is taking math, or, excuse me, being a student who is taking English, right? Those are the 2 main events. These are not independent events. If they were independent, you could either take math or you could take English, but you couldn't take both. But because of the fact that you can take both, in fact, we have 7 students here who are taking both, they're falling into both categories, and so they're not mutually exclusive. So in any case, let's go ahead and take a look at this. So we have two categories, and for each category, you have two states that you can be in. You can either be taking a math class or not taking a math class. You can be taking an English class or not taking an English class. So you have two choices for each thing. So the way we look at this, the way I like to look at this is just make a little table here. Let's try a thing that draws first, right? So here's my table. And across the top, I'm just going to say taking math or not taking math, right? Which would be the complement. And then we have taking English or not taking English. And then we're just going to start sorting these. And then down here at the bottom, I'm going to put some totals. And over here, let's see, we've got totals here. All right. Now, if we look at what we have organized here, oh, actually, let's scoot that up. That was supposed to be higher. We'll put it up here. All right. Now, if we look at this and look at what we're given here, we know that the total for everyone who is taking math, right, has to be 15 because there's 15 students taking math all in all. And the total for the students taking English is going to be 20. Right? So what we're doing here is we're just trying to organize, we're organizing the numbers of everything. Now, we also know that the people taking English and math, I'm going to write that right here, that there are 7 of those people. Okay, now, we have 3 other categories here. Over here in this column, we have people taking English and not taking math. Now, if I add the people taking math, of the people taking English in this row, I know there's 20 of them. 7 of them are taking math and English. So all we really need to do is figure out how many people are not taking math here. And let's see here. So if there's 20 in total and 7 of them are taking both, the number who are taking English but not both has to be 13. Right? That's the only way it's going to add up to 20. And then in this column, same thing. Everyone in this column is taking math. 7 of them are taking English and math. And then there has to be, oops, well, that's fine. There has to be 8 of them left over if I'm going to have 15 people taking math in total, right? Now, because this is a group of students who are taking math and English, that means the number of people who are not taking either should be 0. Okay? Now, that means the total number of people not taking math is 13, and the total number of people not taking English would be 8, right? So we just diced that whole thing down. And there's 2 ways to look at this here, because if we're going to find probabilities, we actually have to figure out how many students there are in total in this category. It's not 35, and I'll show you why. Because 35 is the thing you want to jump to because you're adding 15 and 20, right? But the people who are taking both are being counted in both categories, right? So if I want the number of people taking math or English, right? Remember, that was our notation for this. Math or English, it should be the number of people taking math plus the number of people taking English. But here's the thing. If you have people taking both, like in here, if I look at this English row here, I'm counting this 7 in the 20 I have here. And if I look at this column, I'm also counting the 7 in this 15. So I've counted it in there twice. I only want to count it one time. And so what I have to do with this whole business is subtract out the number of things that are in both, which would be M intersect E. So this right here is an intersection symbol, and that means it's both, right? It's both math and English simultaneously. So the full formula here for the number of things would be 20, which is, oh, I just wrote the wrong thing. I'll stick to the same order. 15, which is the number of people taking math, plus 20, which is the number of people taking English, but I want to subtract out the number of people taking both, right? 15 and 20 is 35, minus 7 is 28. Okay, so that was using this formula here. And you notice that looks very much like the formula for probabilities. If I wanted the probability of math or English, it would be the probability of math plus the probability of English minus the probability of both math and English, right? And so what that means, what that will mean as far as calculating our probabilities, is that it really helps to make this chart because of the fact that it, what's the word I'm looking for? It'll help you organize and remember to subtract that out because that, anything that's in the intersection gets counted twice. Okay, now the other thing that's interesting about that, we just found out that there are 28 altogether. Once you have these totals, right, I'm adding up the rows as I go across. You notice 20 plus 8 is 28. 15 plus 13 is 28. And so that's a good check. You need to get the same number for this sum this direction needs to match this sum this direction. So it's a good check. If you're not getting the same number on both sides, you did something wrong. You need to change it. Okay, so I just made a mess of this. So I'm going to go ahead and erase this and then recreate the table here, I think. Let's do this. Okay, so let's make this table one more time. Math, not math, English, not English. And I believe we had 7, 13, 0, 8, 20, 20. 15, 13, and there we have 20 and 8, and the whole thing was 28. Okay, so that's what we came up with in the previous section there. Now we can actually use this to, once you fill out all these things, you can use it to start finding probabilities, right? If I wanted something straightforward, like the probability that I get someone who's taking math, well, I know there are 20 people taking math altogether. If I want that probability, it's going to be 20 divided by the total number of people that I'm counting, which is 28. And so that will reduce now to 5/7. So the probability of finding someone who's taking just math is 5/7. If I wanted someone who's taking math or English, but not both. Now there are symbols for being able to say that, but it's one of those things. I don't think it was covered in 20A, and it's not a typical thing. So most of the time when you're looking for this kind of a probability, it'll be either written out in a sentence, or you might see something like this, right? And it's fine to do a statement like that. But if we're looking for this, the way you would compute this, the probability is 28, or excuse me, the denominator is 28. So let's see how many people are taking math and English, but not both. Well, you can count them up, right? 8 and 13 is 21 plus 0. That's basically, when we're looking at this, anything that's not both, this, and this are the things we're going to be adding up. And so I end up with 21 here. And if I simplify that, that's 3/4. Oh, and that's actually a complete coincidence that it happens to be three-fourths of the thing too, because typically that's not how it works out. Um, okay, now let's go ahead and take a look at something called conditional probability. We talked about it a little bit earlier, and the fact that the outcome changes depending on what the first thing is. But there's a notation, and I haven't used it yet. If I want the probability, let's see here, I got that on, yeah. If I want the probability that they're taking English, given that they are in a math class, right? That would be written the probability of E given M. All right, it's kind of a weird notation. So that line there means that M is already true. I already know that it's someone taking a math class. What's the probability they're also taking an English class? Well, what that does is it kind of restricts our sample space, because that means that since we already know the students taking a math class, we're looking at only the students taking math classes. And um, over here in our table, that restricts our entire discussion to this column, right? That means that everything we're figuring out is going to come out of that column. I'm not even considering the people who aren't taking math. And so what I'm going to be looking at, if I want the probability of someone taking English, given that they're taking math, I know that the people who are already taking math and in an English class, there are 7 of them. And then the total number of people taking a math class is 15. And so what I end up with for a probability is 7/15, because of the people that are taking math classes, 7 are also taking English, right? There's 15 people taking a math class, 7 of them are taking English as well. So if you're guaranteed that the person you're choosing is a math student, that means all you look at are the math students, and that becomes your new universe. That becomes your new sample space, just for the sake of this particular probability. So it's kind of a nice way to look at things. Now, there's a formula for it, especially when you're looking at a table like this. Um, the probability of some event given another event has already happened, oops, is equal to the probability that both of these events happen. Oop, boy, I'm having real issues with writing the thing I mean to write. Okay, and that is divided by the probability that the condition, the one that's already true, we want the probability of that event, right? So this ends up being kind of a nice formula. Well, let's take a look at this. This is the probability that we have an English student who is also a math student, right? Because this intersection symbol means and. So it's English and math. Well, we know how many people are in that. That's the 7 over here. So that means my numerator is 7. Well, actually, I can write the whole thing, 7 out of 28. I'm going to leave that denominator. That's the probability. And then down here, the probability that someone in this group is taking math is 15 out of 28. Now, if you flip that and multiply, the 28s cancel out, and you end up with 7/15 again. Right? And so you get the same thing whether you're looking at the table and just looking at it to figure it out, or if you're using the formula. It works both ways. The formula is nice because sometimes you're not able to make a table. Sometimes the things are a little bit too crazy. You can figure out intersections with a formula or things like that. But if you have a table, this is a really nice way to go. Okay, so where's my button? There it is. So that concludes our last example here, and hopefully that'll be enough to get you guys through here. And in any case, until our next lecture, keep your pencils and your wits sharp.